It's a pleasure to present here, unfortunately now virtual. I hope everything works out. So what I'm going to talk about is joint work with my now postdoc Stefan Gerster, who's still here in Aachen, and former postdoc of mine, Hui Yu, who's now in Tsinghua University. And so some references in the end, but if there are any further questions on these references, please don't hesitate to contact me afterwards. So what is my interest? So in principle, what we wanted to do is we want to ask a control question, and in particular we are interested in feedback control of typically nonlinear hyperbolic systems or also kinetic equations which have a variety of applications like stabilization of gas flow in pipelines or stabilization of water and so on. So there are plenty of these things, and typically the approach which has been used is that one defines a suitable Lyapunov function and shows that perturbations decay exponentially. And I want to show today how to apply such a framework, how to design such functionals in the setup of linear kinetic equation, which also have a relaxation term. And what I think maybe what is one outcome of this is that in a deterministic case, we are not able to control this in this exponentially fast way. But if we introduce a certain uncertainty in the relaxation rate, then there is a chance to get this. And so far, we have not transferred this yet to a real feedback control law, but today I want to show you what kind of techniques we use to stabilize the dynamics, at least on the full space, and in particular, what kind of functional we used and how this approach worked. But in order to set this a little bit in the framework, I have now actually 1 and 2 slides on the general background. So for this stabilization has been discussed a lot by Jean-Michel Coron and his co-workers, and I wanted, even though it's very simple here, but I wanted to show why this Lyapunov function is interesting and how this can relate to feedback laws. And so the basic problem, if you boil it down to the absolute necessities, is the following setup. You have a linear transport equation, here also scalar, and I have some remarks on the later one, and say A for now is positive. You have 2 boundaries. You can, of course, control the left one. And the idea was, and as I said, there are many references, but you can take, for example, look in this book. The idea is to introduce a Lyapunov function which has a certain weight and takes a weighted L2 norm. And if you multiply and integrate by parts, you see that if the boundary is dissipative, so if this kappa is less than 1, then in fact this Lyapunov function decays exponentially fast. And this result you can use, of course, to stabilize dynamics. So if you have a nonlinear dynamics, you linearize around your desired point, and then you use a cost function like this, and this Lyapunov function introduces certain conditions on this boundary, K, for example, so that perturbations of a state are damped out really fast. And this basic setup has been extended, of course, a lot, and you can have more complicated boundary conditions, nonlinear dynamics, you can have systems, you can have networks, you can have uncertainty. However, one point which I want to stretch is the following. So usually, of course, the control of the nonlinear system is interesting, and the way it works with this approach is by linearization. So if you have something nonlinear, then you can essentially control in a neighborhood of this linearization point. And of course, the natural question is, if you think of this as a nonlinear hyperbolic balance law, why don't I approximate this with a kinetic equation and try to find control or try to find Lyapunov functions which are also stable in the limit and which give me some feedback control also in the limit of small relaxation limits. And this is how we came to this setup. And the simplest problem may be a two-velocity relaxation model would be the following. So you have now 2 components. One is transported from left to right, the other from right to left. And you have a linear source term here with a small parameter, epsilon, which you want to drive to 0. And of course, there is a global steady state for this problem, and you have a transport like this. So sorry, this should be dx, of course. So there's a dx missing here. It's really transport, and there is this source term. Everything is linear. If you would now apply this theory, which I had on the previous slide, you will see that the cost function we had before will not decay. There's no way, because the source term doesn't have the proper sign. There is not dissipative with this one. However, you can also already see from the notation I chose here, this is kind of what we want to apply. So in the setup of this kind of equations, you have, of course, this hypocohesivity framework, which would give you an estimate of the solution deviating in some norm, which I have on the next slide, from the global steady state in terms of an exponential factor, a constant, which also depends on this rate epsilon, plus the distance of the initial data. However, if I look at this from the perspective of also having something in the limit epsilon to 0, then you can see for this small problem, you can explicitly compute all of these things. And I have here a small picture, numerically computed these values. And I look now, the blue line is the k of epsilon. And what you see is when epsilon tends to 0, well, the k of epsilon tends also to 0. And so you lose your nice property of exponentially damping out possibly perturbations in the limit. And so the question is how can now, so first I will now introduce maybe this hypocohesivity framework, but only shortly, just to set up the notation. And then I will discuss a little bit on how to regain, say, a positive decay rate for an exponential decay of states deviating from some steady state in this linear kinetic setting, with having in mind to extend this to boundary control and to also the limiting case when epsilon to 0 for nonlinear equations. So using this as essentially a different way to approximate nonlinear equations by linear systems. So even though many of you here probably know this setup, I want at least to have 1 or 2 slides on the notation and on this hypocohesivity framework. And I use essentially the same notation as in this paper of 2015 from Moreau and Schmeisser. So we will look at kinetic equations, which have these linear kinetic equations, which have this transport term. They have a scaling here. The interesting case will be alpha equal to 1. I have later slide to say how this alpha influences these rates. And you have a linear source term, and you have initial data, which is always called F0. The global equilibrium of the source term L is denoted by F, as before. And there are conditions on T and L, which I have on the next page, which ensure that you have for this equation an estimate like this with these exponential factors, which have the same notation as before. And I said that this is related, that we are interested in somehow using kind of Lyapunov function, and this estimate is obtained using Lyapunov function. So this gamma is non-negative and is entered in this what's it called, modified entropy functional, where you have a norm which is a weighted L2 norm with a weight which depends on the steady state, plus this product of this operator, which where the P it appears, and P is a projection of F to the null space of your source term. So this, as I said, so this notation is taken from that paper, and the conditions under which you now obtain this decay, which is stated here on these operators, are again given here. I will not discuss those in detail, but I will need them later, and therefore I wanted to state them. You have 2 cohesivity properties, one on the microscopic, so on the level of F, and then one on the level of the projected F, and then you have boundedness assumptions on some operators. And again, let me point out that in the case alpha equal to 1, so this acoustic scaling, in general, you observe that the k epsilon for epsilon to 0 tends to 0. And so this brings me to the next slide which says, okay, how are the results in the limit in general? So I said we have this scaling, and if you have alpha equal to, sorry, I said it wrong. Alpha equal to 1 is parabolic scaling, so you have a higher scaling here than here. Then it's already been shown that even in the limit, you get exponential decay with a positive decay rate, which would happen. So, and this result has been also extended to random relaxation parameter, which is somehow sampled from some given distribution. And then you have a similar result now in expectation. So expectation with respect to the randomness of this parameter. However, in the acoustic case, you have the same result as I had for my toy problem. So in general, the rate will vanish in the limit. And this is something we somehow from a conceptual point, we want to somehow relax a little bit. And so what I'm going to do is I will present, of course, a weaker result, but in the acoustic scaling, and I modify the problem slightly in order to also regain exponential convergence in some in a weaker sense of this limit. And the idea is the following. The idea is that we take now acoustic scaling, so we have only the 1 over epsilon here. And so we replace this 1 over epsilon by a parametric uncertainty, which is called xi, and some small, can be arbitrary small number eta positive. And consider now this equation, which is here in the second line. You can see it. Which is now a random equation, so the f depends on this additional uncertainty xi, which is parametric, so it's written in all these arguments, and the xi appears here. And now we mimic the case that epsilon tends to 0 by allowing that the realizations of xi tend to infinity, which just means that the xi has somehow unbounded support. And so we have this small eta here. I think this is also on the next slide, because of course the xi can also have realizations which are 0, and if eta would be 0, then we would have lost completely the influence of the source term, but we need the source term in order to recover somehow our nice limit. So therefore we need a deterministic eta positive, and we take a xi with unbounded support. Our assumption is still that the as in the parabolic scaling, that the equilibrium is deterministic, the initial data is also deterministic. This equation is now a random kinetic equation, so it depends on this additional parametric uncertainty, which has unbounded support, and clearly there are plenty of references, and I have not written any here, but I'm happy to give them to you on these things. And the question is now, can we, for this equation, gain somehow an estimate which would allow us exponential decay? And let me comment a little bit on what we take as assumption. So I said that the eta has to be small but positive in order to prevent the complete loss of the source term in case of realizations which are 0. I also said that the xi has to have unbounded support. So what are distributions which fulfill this? Not sure if this is big enough for you to see, but there are pictures of realizations of xi. So you can have exponential distribution, you can have Erlang or xi squared distributions. These are the realization of xi. These are the realizations of xi plus eta, where you can see the shift in eta. And so what we took, and this is now crucial, so because our results depend in some sense on this choice, so we took xi, which has a probability density, which is parameterized by alpha, bar, and beta. It's not important what these values are, but with these values you can control if you are either exponential or xi square or Erlang distribution. But so we take xi, which is distributed with this probability density. And we use, later in the proof, we use particular properties of this probability density. More precisely, we use properties of the orthogonal polynomials to this probability densities, which are these Laguerre polynomials. So this is a crucial part. So our results are really only for noise in some sense, which has this distributions, because we use properties of the orthogonal polynomials to this density. Then the next question you can ask is, okay, so I have now replaced my small epsilon problem by a problem of large psi, essentially, but now I have a random problem, so I have an additional parameter. So in which sense do I want to obtain exponential decay? And we do it in a similar way as for the parabolic case with random relaxation parameters. So we look at the expectation of the squared deviation from the deterministic steady state, which is this integral, and this norm here is precisely the same norm as in the hypercohesivity framework. So this is again a norm, L2 norm, weight with respect to x and v, weighted by the equilibrium f. And so if you have a problem like this, so you want to, I don't know, compute or show that this decays exponentially, and you have this additional equation, you say, okay, well, it's not particularly challenging, maybe because it's just another transport equation with an additional phase variable, which appears also here as a first term. And so the simplest way would be the second one, what is called a non-intrusive way. You say that you just sample psi from your distribution, and then for each fixed psi, you apply the hypercohesivity framework from before, because the operators are precisely the same as in the deterministic case. And then you compute these expectation by essentially using the average. If you would do this, and I have a picture on the next slide, then you don't see any exponential decay. You end up with the same problem as before. The decay rate will tend to 0 for these larger and larger realizations which you get. So this is not maybe the preferred way. So therefore we pursue these, what is called the intrusive way. So we use a series expansion, so a generalized polynomial chaos expansion with respect to polynomials. And these polynomials are now the ones, these Laguerre polynomials. They are the ones which are orthogonal to this P. And so we obtain a system. I will show the system in a minute, but the basic idea is you substitute, of course, the series in here, you test against the orthogonal polynomials, and you get an enlarged system of kinetic equations for the coefficients of the series expansion. And before I show you this system, I will show you the numerical result on the toy problem. So you have on the right, you have no exponential decay for the non-intrusive case. And so you see that this somehow tends to 0. This rate, this blue rate, which is essentially the expectation of the coefficient of the decay, the exponential decay, which you expect. And in the GPC case, so in the intrusive case, you see that it is also decays and also to quite low value, but there's a lower bound. Right? So you get exponential decay in the intrusive case, but not in the non-intrusive case. And I want to elaborate a little bit on this and how we got to this result. And this is a computational result, but we also have, of course, an estimate for this K, for this lower bound. And this computational result is for this two-velocity model, but the results I'm going to show now on the theoretical part, they hold under these general conditions on T and L. So what do you have to do? Well, the first thing is that, okay, you have your deterministic system, which you expanded by this by this additional uncertain variable. And then I said that you now take this GPC expanded system, so you apply the series expansion, you test, and you get an enlarged system. The initial data is deterministic, so the initial data will only appear in the first component. This is indicated like this. And then you have, of course, all the other components of your series expansion. There's not yet any truncation done, so we have just written this as an operator equation for this f for the coefficients. And now the question is, what are these operators? So this bold T and the bold L, they are the operators which come out, of course, out of T and out of L. And so the T, nothing changes. So this T is in fact the operator T, but now for each of these coefficients. In L, it's a little, there's a little difference because you have as operator psi times L, So what you get is you get a multiplication with a matrix which is this pk, which has entries pki, which are in fact the integral of this Galerkian product with psi with respect to this probability density. And this p, somehow these properties of this p are exploited in order to show exponential decay. And then you have the other part, which is eta times L, which just gives you again this L operator copied to the full space. So now, in which space do we get any estimates? And so the point is that, as I said, so we use the properties of this P, and so we look for solutions which belong to a weighted space. So, and the weight is the sigma k. And here you can see alpha bar and beta. You probably don't remember, but these were parameters of the probability density P. So I said that we can do that for unbounded noise psi, which is given by certain distributions, and those distributions are essentially parameterized by alpha bar and beta. And so this term really appears here as somehow as a major influence. And then you have also this eta, but eta is a fixed parameter. Yeah, it can be small. And so what we are looking for is essentially vectors of coefficients such that a weighted L2 norm, so this is then again this norm on xv with the weight 1 over f, that says this weighted L2 norm is bounded. And then we can show that the coefficients of these systems, fulfill a bound of the following type. So you have this f bar in this L2 sigma space is bounded by the initial data f0, which of course also belongs to this space, but which also has only one component. And this bound is, of course, this is a crucial part. This is linked to the particular properties of this probability density. Clearly, if you have an f which belongs to this space, then it also belongs to the space L2 without a bound. And we have also this inequality which tells me that this is bounded by this norm for all f which belong to this smaller subspace. So what is one point why we get this exponential decay, if you want, is that we somehow have a better control about the solutions, which and this about the decay of the higher mode of the solution compared to a somehow Monte Carlo method where you would just sample and you would have no control on this distribution in f. This is, I would say, one of these things. Now, the second is, of course, now you have to check that these operators which you have defined still fulfill the hypocohesivity framework. So, and I don't give any details here, but the basic result is the following. These conditions H1 and up to H4 and these operators T and L, they essentially imply that also these bold operators T for the system of the coefficients and this operator L, which is not just L, but also L plus, maybe I should show it again, L plus L, which is L plus L times P, that they also fulfill these conditions. And then you can essentially apply this hypocohesivity result now to this extended system. And this then gives you, after some computations, essentially exponential decay of the expectation with a constant kappa, which is now bounded from below. This was this KE in this previous plot, and I have it again. One more thing. So here again, this decay will be in this. So the solution of the SD bound we had before, as I said, was in the smaller space. So there's a stronger bound. This decay is not in this. Yeah. So we have somehow here this. We have here decay in this original L2 norm, but we have it for. But we know that the solution to this enlarged system belongs to this smaller space. The second thing is, and this is actually crucial when you now do the numerics, is the following. This is a result which holds in principle for any size. So we have no truncation. But of course, if we want to run this numerically, then we have to truncate the GPC series at one point at k. And then there's, of course, an error between what we have approximated in the subspace K and the infinite series. And we have actually control on this error, also due to the fact that we know precisely what kind of distribution this original psi has. And what I want to show is now somehow two numerical results which highlight these two remarks. So the first one is that I said that we have exponential decay only in this L2 space, but not in this stronger L2 sigma space. And this you can see also numerically, because here, so this is the expected decay, so the slope in this blue dashed line, and this is the numerically observed decay. And you see that you are always smaller, except at high times, at large time t, where somehow this line now crosses, so the diagonal would be below this. So, I mean, it's a small, you have to zoom in here in order to see it, but actually you also see numerically that we cannot expect the exponential decay in this stronger space. The second is the following. I said that there is a truncation error. So we can show that the truncation error between a series which only runs to order k and the full series behaves like a constant with some power, which we can also specify, and then times t. So the longer it runs, of course, the worse the error gets. And this you can see essentially in the first part of this picture. So here you see the truncation error over time for the toy problem. So again, two velocity model, and we run it up to time 20, and we compare with the larger solution we have. And you see for the different truncation errors 1, 5, 10, 15, and 20, how the error over time somehow propagates. And of course, as expected, this gets worse. On the other hand, if you say that you are interested in the solution at a fixed time, then you can of course look at a fixed time, and you can increase truncation order, and then you see how the error decays when k gets larger. Okay, and you see this here for time 5 and here for time 20. And here the scaling is 10 to the minus 1 up to 10 to the minus 7, and the same here. So we have these competing effects. Of course, we have the truncation error, which increases, but which we can control essentially by this estimate, depending on the given time. And we have exponential decay in, let me go back, in this L2 norm, but not in the L2 sigma. Okay. Yeah. Finally, of course, I want also to show that if we now fix some time, say here time 20, I want to show that you can also observe this numerical that you can also observe this exponential decay numerically if you have a sufficiently high degree of truncation. So you have here again the lines in the color with truncation 1 in blue, and then up to pink for k equal to 20. We have, as a reference, we have a high resolution result for I think 100, k100 series, which is here the black dashed line. We have the Monte Carlo, which is called here quadrature result. And then you see these exponential decays for the solution also in this period, and also, of course, here in these parts. And so this is now a system which is solved in the intrusive way with 2k coefficients. Yeah, I think my time is almost up, so let me just come to the summary. What we did is, so far you have not seen our feedback control law, but what we did is we extended somehow the acoustic scaling setting to parametric uncertainty in order to avoid this decay in order to avoid the degeneration of the decay rate when epsilon tends to 0, and we recovered that by using this stochastic method. Clearly, this is a weaker result in the sense that We have now unbounded noise. We have a particular unbounded noise, which includes some distributions, but it's really focused on that. What is interesting is that maybe the intrusive approach allows to get these exponential decays, but the non-intrusive does not. And this is strongly related to the fact that somehow for the intrusive approach, we can get a better bound on the solution. The next step would clearly be, of course, to use that now on a bounded domain to derive, as in the beginning shown, maybe suitable feedback laws for the boundary, for example, or to somehow extend this in the sense to a nonlinear setting that we say that we want now to control this limit. These results, which I've shown here, I'm happy to share also the preprint, will appear in this paper. And as I said, this is joint work with my students, Stefan Gerster and Guillaume. Thank you very much for your attention, and I'm happy to take questions.
Thank you, Michael. Any questions? Okay, let me start with. So you mentioned that for intrusive method, you don't get exponential decay. Are there any intuitions on why that's the case, even including a stochastic collocation method?
Yeah. So for the non-intrusive, I don't get this because what is crucial, in my opinion, is the following: that if you study this expanded system, you get a better control of the space in which the solution lies, right? So we get really we have deterministic data and deterministic steady state. And so we can really control the higher order modes and can show that these higher order modes are somehow decay sufficiently fast. And this we exploit in order to get the exponential decay. And the non-intrusive, I don't have this knowledge, right? I just have samples according to a certain probability, and I cannot get a better result. I mean, maybe it's. I mean, I will not. Don't want to include as is impossible, but if you do just a sampling strategy, then you don't see this decay.
You talk about the Monte Carlo samplings, but if you do stochastic looking, I mean stochastic collocation.
If you do stochastic collocation, then the question is here. Okay, then there's another point. I mean, then you have to balance. I told you that this, or I said that maybe I should be clear. So this result is a result on the infinite system, right? So if I do additional truncation in this one, I get an additional error, which I've shown in the end, which also increases. So if you do collocation, it's in some sense the same as doing a series expansion and truncate at some point, which corresponds to the number of collocation points you take. So if you do stochastic collocation, then you have somehow to balance also, to do a detailed analysis how to balance the truncation order or error against somehow the remainder which decays exponentially. So it's not, I would say it's not so straightforward to then distinguish these two effects. But in principle, of course, it should be possible in this sense.
So you mean the non-decay comes from the post-processing, right? It's sort of an interpolation, and I mean those steps destroy the exponential decay. That's what you have.
Could be, yeah. Yeah. So, okay, what we have not done, to be clear about this, so we have not analyzed this stochastic collocation case, okay? And for sure would be interesting to see, but I think one has, as I said, one has to balance these two things in a proper way in order to not deteriorate this result. And in the intrusive case, this is of course much easier because somehow these operators regain the nice properties which you already have, and so it's yeah. Another thing is that yeah, so we use actually heavily the fact that we have a particular noise, right? So this and these Laguerre polynomials, this really enters. So this yeah, of course this you respect also when you do the collocation, but it's not completely clear at the moment to me how to utilize this in order to prove this for a different case.